correction list on Avenue to Learn. So if you go to Avenue to Learn, you will see a student number on the left column, and then you will see the grades related to the student number. Okay. So I was told that on the 25th, you'll have your stats. Am I right? How many of you are taking stats? So all mechanical engineering second year have stats. Am I right to say that or wrong? So all those engineering and management, you have no stats. Am I right? Okay. So tentatively, the date is on the 25th. I already booked the rooms. Okay. I'll try to move it to the 26th. You all have anything on the 26th? Anyone? Okay. So tentatively is 26. Okay. So only 38 students fail. Okay. Which is thank God. And the class average was 61. Okay, so if you get more than 61, you're fine. If you get less than 61 to 50, you're struggling a bit. If your name is on the list or your student number is there, just work hard. What else? Now, some students will be in a range of, so how the correction works is you have to score 100% to get a 50%. Okay, that is why it's called a correction. We clear? I used to not do that, so students just do enough to get 50 and then they pass, but they did not learn anything. Okay, so you have to score 100 to get 50. The best grade that anyone fail is a 50. So any student, I'm not saying that it's you, but any student that you get 13 out of 30, I wouldn't do it. You get where I'm coming from, right? If you get 13 out of 30, in order to get a 15, you have to get 100%. I'll let it go. Okay, those of any student that is below 10, okay, I'll strongly advise you to take your corrections. Are we clear? Okay, so that is what corrections is all about. Okay, the question will be exactly the same. No change, no nothing. Okay, will be exactly the same, and you just come in and you write. Okay, as I say, tentatively, I have to change the date. I realize that some of you have a stats course. Okay, right. So today we are going to do something different. No more mole circle. We will come back to mole circle later on. Okay, we're going to apply mole circle later on. So today we are going to look at normal stress induced by bending moment. So it's more of a what do you call that? Revision. Okay. So some of you have taken 2P last term. It will be very quick. Those of you who are in engineering and management, you're like, oh, I've taken this about a year ago. I can't remember. Okay, don't worry. I'll get you up to speed. Okay, so there are four different configuration of bending moment induced stresses or induced normal stresses. Okay. So if I were to write out the general formula, right? So if the general formula is stress X will be equal to Px over A plus by My over Iyy multiplied by Z. Sorry, make it plus minus. And plus minus Mz over Izz multiplied by Y. Okay. So this will follow a configuration like this. where this is X, Y, and Z. And we have a structure looking like this. This is just an example. Okay. So the direction of stress X, as you can see now, we are looking at stress X over here. Okay. So if we were to put an element like what we have learned before, okay, so this is, for example, this is an element now. To make you relate that what we have just learned, okay? So that is the general form of the formula. So in bending moment, there are four, as I mentioned before, there are four different configurations. One is what we call centric, symmetrical, bending. Okay. And then the second one is what we classify as eccentric, symmetrical, bending. And the third one is what we classify then as centric, unsymmetrical, bending. And the fourth one is our eccentric, unsymmetrical, bending. Okay. So if we were to write the general formula for this, right? And I'm going to build up on the formula. So let's say we have stress X in condition number 1, stress X in condition number 2, stress X in condition number 3, stress X in condition number 4. If we have something that is known as eccentric, we always have the term Px over A. So i.e., anything that is eccentric has a axial loading and bending moment components. Okay. Now it comes to the next term that you'll see, symmetrical and unsymmetrical. Yes or no? So those that have you that have done 2P, Dr. Koshi will use the term symmetrical and what? Unsymmetrical. Now, when is it symmetrical and when is it unsymmetrical? Okay, so I'm going to draw cases, okay, and you tell me, is this symmetrical or unsymmetrical? Okay, and we start from there. Okay, so now if we look at, I'm going to draw 3 different loading conditions. Okay, so the first one looks like this. So number 1, okay, before I do number 1, I'm going to declare that this is our X and this is our Y, followed by our rotation in the Z. Okay. So this is number 1. Number 1, you have a load looking like this. Okay. Right. Point A, point B. Okay. And then the second one, we have a load looking like this. Point A, point B, okay? And case number 3, we have a load looking like this. And I'll declare that from here to here is L/2, and from here to here is L/2, and this is our L. From here to here, this is L/2. From here to here, L/4. From here to here is 2L. And then from here to here is L. Okay. Then the next thing that I'm going to draw for you, okay, we are now going to look at the cross-sectional area. Okay, so we have our cross-section. So each of them will have 3 different cross-sectional area. Okay, so sectional area number 1, it looks like this. Okay, so when I'm drawing this, can you please draw in the transformation? This is Y and this is Z. Cross-sectional area number 2 looks like this. Cross-sectional area number 3. Running out of ideas. It looks like this. Okay. And then this is our rotation about X. Okay. So on the cross-sectional area, I want you to label this as, what do I call it? Alpha, beta, I, and J. Over here, alpha, beta, I, and J. Alpha, beta, I, and J. Okay. So each loading condition, okay, you can have 3 different cross-sectional area. Now, let's look at the loading condition. We have number 1, number 2, number 3. Listen to me. Which will induce symmetrical bending moment? 1, 2, or 3? Anyone? Yes. Okay. 3. Okay. And why do you say 3? The loading is symmetrical. Okay. So we have pinpoint 3 is the loading that is symmetrical. Okay. So 1 and 2, we declare that for now, we declare it as unsymmetrical. Okay. Now, the cross-sectional area now, 1, 2, and 3, which will induce symmetrical bending moment? Cross-sectional area 1, 2, or 3? The only one that's around, which one? 1. Okay. So 3 is symmetrical, 1 is symmetrical. How many of you agree? Right? How many of you don't agree? I'm going to murder Dr. Koshi. All of them are symmetrical loading. You're not wrong, you're right. How we define symmetry in bending moment is you, first of all, most of you define it as if the left-hand side and the right-hand side on the 3 different bending conditions are the same, you declare symmetry. Nothing is wrong. Okay, you're right in that context. And then if you look at the cross-sectional area, when the left is equal to the right, you declare symmetry. Okay? We're going to visit Dr. Koshi after this. The right answer is all of them are symmetrical. All of them are centric symmetrical bending. I'm going to prove to you why now. Okay. If we were to look at the formula now, or before we look at the formula, I'm going to look at the cross-sectional area now. Okay, we are going to look at the cross-sectional area. So the cross-sectional area, okay, I'm going to draw down here. This is our neutral axis. Okay. Over here, this is our neutral axis. And over here,